Good day, and today we're going to go over Bayesian networks. What exactly is a Bayesian network? It's a graphical representation of probabilistic relationships in a graphical network. So let's say we have a G, a child T, and T has its own children C and D. This is a directed acyclic graph, meaning there's no cycles, and they're only directed edges, which indicate dependencies in the graph. And this graph would come with something called conditional probability table, which indicate the numerical probabilities of these relationships. All of these constitute a Bayesian network. And what can we do with a Bayesian network? We can conduct inference. Inference is, for example, it's conducting the probability of C given G. So we're trying to find a probability given information in the graph. Now, how do we do this? I want to introduce something called variable elimination, which is a type of methodology of exact inference that we can use, especially for smaller graphs, and it can save computation. So here, what we can do is we can do marginalization. So it's a way that we can sum other variables in the network. So here, A and T, and we can expand this to be the joint of C, A, and T given G. And we're adding A and T because both of them, so C has a dependency on T, and T has a dependency on A and G. C doesn't necessarily have a dependency on D because once it's given its parent, that's all that's needed for C. Now here we can use both product rule as well as conditional independence to expand this expression out. So this becomes the summation over A and T times the probability of A times the probability of T given A and G times the probability of C given T. We did two steps here. We did a chain rule of taking probability of a variable in the joint given the evidence, and then the next variable would be the probability of that given the previous variable, as well as the evidence, and so on and so forth, as well as leveraging conditional independence, saying that node is only really dependent on its parents. So now what do we have? We have probability of A, which would be given in the CPT. Same with the probability of T given A and G, probability of C given T. Now here's where variable elimination comes into play. We can expand this summation as the summation of over little a of probability of A times the summation over little t, probability of T given A and G, times probability of C given T. So here we have an inner summation, which is being summed over little t. This would be a function of A. The reason that is because T is being summed over, and then G and C are provided in the inference. So this is a factor of A, and this factor can be used in the outer expression. So once we compute what this factor is, we can use it to find the probability of A times this factor and sum it over little a. So these factors are really useful because once we have longer expressions that may be more complicated, they may have repeated computations, and we can save those computations by reusing these factors. So for exact inference, variable elimination can be really useful, especially when you compare to doing brute force calculations and doing the same calculation every time. So I just wanted to go over very quickly what Bayesian network is, what we can do with it, such as inference, and then how we can go about doing that. And thank you so much for your time.